If you sit very still and place 2 fingers against the inside of your wrist, you can feel the rhythmic, insistent thrum of your own pulse. It feels like a constant, a fundamental baseline of being alive that you probably haven't thought about since breakfast. But why does that rhythm have an expiration date? Why is it that your heart is biologically scheduled to beat about 2.5 billion times before it simply stops, while a tiny shrew will burn through its entire allocation of heartbeats in less than 2 years? Why does a housefly get a few weeks of buzzing against a window pane, while a Greenland shark can spend 4 centuries drifting through the silent, freezing dark of the North Atlantic? Is there a secret mathematical formula hidden in our cells that decides exactly how many sunsets we're allowed to see? Why do some animals seem to have hacked the system of time itself, while others are forced into a frantic, high-speed race against an early grave? And if we could figure out exactly how they do it, would we realize that our own lives are actually much shorter, or much longer, than they were ever supposed to be? But maybe focusing on the heart is looking at the wrong piece of machinery entirely. For a long time, scientists believed in something called the rate of living theory, popularized by biologist Max Rubner in the early 20th century. The idea was elegantly simple. Every animal is born with a finite amount of energy, like a battery that can't be recharged. If you use that energy quickly, your life is short. If you use it slowly, you live longer. It's why an elephant with a heart that thumps a leisurely 30 times a minute can live for 70 years, while a mouse with a heart racing at 600 beats per minute is lucky to see its 3rd birthday. Does this mean that if you just exercised less and slept more, you'd live to be 200? Unfortunately, the math doesn't actually hold up when you look at the real outliers of the animal kingdom. While the metabolic rate definitely plays a role in how fast our biological clock ticks, it's not the whole story. If it were, then every animal of a similar size should have a similar lifespan. Why, then, does a common pigeon live significantly longer than a rat, even though they weigh roughly the same and have similarly high-speed metabolisms? Why does a naked mole rat live 30 years in a tunnel while a brown rat of the same size dies of old age in 3? Actually, the idea that metabolism is the primary driver of aging is almost completely undermined by the existence of birds and bats. You would expect these small, high-energy creatures to burn out like cheap light bulbs within a year or 2. Flying is an incredibly expensive activity from a biological perspective. It requires an immense amount of oxygen and generates a massive amount of metabolic waste. Yet, some species of bats can live for 40 years. How is it possible for a creature the size of a thumb to outlive a large dog? Researchers like Dr. Emma Teeling have spent years studying bat genomes to find the answer. It turns out that because bats evolved the high-stress ability to fly, they also had to evolve elite-level cellular repair kits. When we burn energy, our cells produce free radicals, nasty little molecules that bounce around and damage our DNA like shrapnel. Most small animals just soak up that damage until they fail. But bats? They have evolved unique ways to suppress inflammation and repair that DNA damage on the fly, literally. This suggests a provocative question. Did longevity only happen because these animals needed to survive the very thing that should have killed them? Is a long life just a side effect of being built to handle extreme physical stress? But even that elite repair system doesn't explain why some animals don't even seem to try to stay healthy, yet they live for centuries anyway. This brings us to the Greenland shark, a creature that makes the human lifespan look like a lunch break. For a long time, we didn't even know how old they were because they don't have the typical growth rings in their bones that most fish have. In 2016, a team led by Julius Nielsen used radiocarbon dating on the eye lenses of these sharks, specifically looking at the proteins that formed when the shark was just a pup. They found a female that was estimated to be nearly 400 years old. She was likely swimming in the ocean when the Mayflower landed in America. Why does a shark get to see the rise and fall of entire empires? Part of it is the cold. The Greenland shark lives in water so near the freezing point that its entire biology moves in slow motion. It grows about 1 centimeter a year and doesn't even reach sexual maturity until it's about 150 years old. If your life moves that slowly, does time even feel the same? Does a 400-year-old shark feel like it's had a long life, or does the cold just stretch the seconds out so thin that they don't count? Of course, blaming the cold is a bit of a cop-out when you consider the giant tortoises of the Galapagos. They live in the sun, on dry land, and can easily breeze past their 150th birthday. So, if it isn't just about being cold and slow, what is it? This is where evolutionary biologists like George Williams and Thomas Kirkwood introduced the disposable soma theory. They asked a different question. Not how do animals live long, but why would evolution bother making them live long? If you're a mouse, you're probably going to be eaten by an owl or a cat within 6 months. In that dangerous environment, there is zero evolutionary incentive for your body to invest in expensive long-term DNA repair. It's better to put all your energy into having 20 babies right now. But if you have a massive, hard shell like a tortoise, or if you can fly away like a bird, or if you're a 3-ton whale that nothing can eat, your external risk of death drops significantly. Suddenly, it makes sense for your body to invest in the high-quality biological materials needed to last 100 years. This suggests an unsettling possibility. Is our lifespan not a limit of our biology, but simply a reflection of how dangerous our ancestors' lives used to be? If we had fewer predators 10 million years ago, would we naturally live to be 500? But even the most protected animals eventually break down, unless you happen to be a naked mole rat. These bizarre, hairless rodents are perhaps the greatest mystery in all of gerontology. They live in underground colonies, they feel almost no pain, and they almost never get cancer. While a normal mouse's risk of dying doubles every few months after it reaches maturity, a pattern known as the Gompertz-Makeham law of mortality, the naked mole rat completely ignores this rule. Its risk of dying doesn't increase as it gets older. It's essentially biologically immortal, in terms of its aging curve, only dying from accidents or starvation rather than old age. Researchers like Dr. Vera Gorbunova have discovered that their cells are packed with a specific type of high molecular weight hyaluronan, a gooey substance that acts like a biological cage, preventing cells from crowding together and turning into tumors. They have essentially built a chemical wall against the very diseases that kill the rest of us. But if a rodent can evolve a way to stay cancer-free for 30 years, why can't we? Is there a reason why some species are allowed to keep their youth until the very end, while we have to spend the last third of our lives slowly falling apart? Actually, looking at the mole rat makes our own human lifespan look like an incredible success story that we take for granted. If you compare us to other mammals of our size, we are massive outliers. A mammal of our weight should technically live about 30 or 40 years. Instead, we frequently hit 80, 90, or 100. Why did we get the longevity upgrade? Many scientists point to the grandmother hypothesis. Because humans take so long to grow up, we needed older generations to stay alive and healthy to help raise the young and pass down complex cultural knowledge. Our long lives might be the result of a biological contract, where the elders are kept alive because their brains are more valuable to the tribe than their reproductive organs. But that still doesn't explain the bowhead whale. These giants can live over 200 years, and they have trillions of more cells than we do. Mathematically, they should be riddled with cancer by age 10, because every cell division is a chance for a mutation to occur. This is Peto's paradox. Why don't big animals get more cancer? The answer is that bowhead whales have evolved multiple copies of tumor suppressor genes. They are walking, swimming biological laboratories that have perfected the art of genetic self-correction. If we have the same basic DNA as a whale, why haven't we figured out how to flip those same switches? But perhaps the most frustrating thing about studying longevity is the realization that for some animals, death isn't even an inevitability, it's an option. Take the hydra, a tiny freshwater creature that looks like a piece of string with tentacles. If you cut a hydra in half, it doesn't die, it just becomes too hydrous. They possess a seemingly infinite supply of stem cells that constantly refresh their entire bodies. Barring a predator eating them or a dry spell in their pond, a hydra could theoretically live forever. Then there's Turritopsis dohrnii, the so-called immortal jellyfish. When it gets stressed, sick, or old, it doesn't die. It reverts back into a polyp, essentially turning itself back into a baby and starting its life cycle all over again. It's the biological equivalent of hitting the reset button on a video game right before the game over screen appears. If the blueprints for immortality already exist in the water right now, why did evolution move away from them? Why did more complex animals, like us, trade the ability to live forever for the ability to have complex thoughts and emotions? Was death the price we had to pay for being interesting? But before we get too deep into the philosophy of mortality, we have to address the sheer variety of ways long life actually happens in the wild. It isn't just one secret, it's 1,000 different patches for a leaky bucket. Some animals, like the ocean quahog, a type of clam, live for over 500 years simply by having the world's most boring lifestyle. One specimen, nicknamed Ming, was born in 1499 and was still alive when researchers found it in 2006. It lived through the Reformation, the Industrial Revolution, and both world wars by sitting in the mud and barely moving. It has a metabolism that is so incredibly efficient it produces almost no toxic byproducts. Is that the trade-off? To live for half a millennium, do you have to be a clam? Does the universe offer us a choice between a short, vibrant life full of movement and heat, or a 500-year life of sitting in the dark and doing absolutely nothing? Actually, even that lazy strategy doesn't explain the longevity of certain birds like parrots. A macaw can live to be 80, and they are anything but boring. They are loud, social, and incredibly intelligent. This has led some researchers to investigate the cognitive buffer hypothesis. The idea is that being smart actually helps you live longer because you can navigate complex environments, avoid predators more effectively, and find food when things get tough. There's a direct correlation in many species between relative brain size and lifespan. Intelligence is a high-cost investment that takes a long time to pay off. If you're a bird that's smart enough to solve puzzles, your body needs to stay alive long enough to use that brainpower. This suggests that our own long lives aren't just about grandmothering, but about the sheer complexity of our minds. We live a long time because it takes a long time to learn how to be a human. But if that's true, why do some of the smartest animals on Earth, like octopuses, only live for a year or two? They can solve mazes and recognize faces, yet they die almost immediately after laying their eggs. How can a creature be so brilliant and yet so biologically destined to self-destruct? This brings us to the dark side of longevity, the programmed death theory. Some biologists, like August Weismann, argued that animals die to make room for the next generation, so that evolution can happen faster. If nobody ever died, there would be no room for new mutations, and the species would eventually go extinct when the environment changed. In this view, aging isn't a failure of our cells, it's a feature. We have death genes that actively shut us down to ensure the survival of the species as a whole. It's a selfless act on a molecular level. But most modern scientists disagree with this. They see aging more as neglect. Evolution only cares about you until you've successfully raised your offspring. Once you're past reproductive age, you become invisible to natural selection. Any genetic glitches that happen to you at age 70 don't matter to evolution because you've already passed on your genes. We are like cars that were built to last through a 5-year warranty. Once the warranty is up, the manufacturer doesn't care if the bumper falls off. We are living in the post-warranty period of our biology. But if we are just neglected machines, why are some of us built so much better than others? Even within a single species, the variation can be staggering. Why did Udvata, an Aldabra giant tortoise, live for 255 years while other tortoises in the same enclosure died at 100? Why do some humans live to be 120 while eating bacon and smoking, while others die at 60 despite running marathons? This is where the study of epigenetic clocks comes in. Researchers like Dr. Steve Horvath have found that our DNA has chemical tags called methyl groups that change as we age. By looking at these tags, scientists can predict your biological age with incredible accuracy, regardless of your chronological age. Some people are literally aging faster than the clock on the wall, while others are slow agers. What's fascinating is that many of the animals we've talked about, the whales, the sharks, the mole rats, seem to have found a way to stabilize these tags. They aren't just avoiding disease, they are actually keeping their DNA young for longer. Actually, that makes it sound like aging is something we can just solve with a clever enough pill. And to be fair, that's exactly what a lot of people are trying to do. Researchers are looking at senolytics, drugs that can identify and clear out zombie cells. These are cells that have stopped dividing but refuse to die, instead sitting around and secreting inflammatory chemicals that age the tissues around them. In mice, clearing out these senescent cells has been shown to restore hair growth, improve kidney function, and extend lifespan. It's like taking a rusty old engine and cleaning out all the carbon deposits. But the more we learn about the extreme survivors of the animal kingdom, the more we realize that their longevity isn't just about one trick. It's a fundamental, ground-up rebuild of how life works. A bowhead whale doesn't just have one anti-cancer gene. It has a whole symphony of them working in harmony. A Greenland shark doesn't just have a slow metabolism. It has a cellular structure that thrives in the cold. We are trying to patch a leaky dam with band-aids, while these animals were built as solid concrete from the start. So, does this mean we're stuck with our 80 years while the clams get 500? Why should we care so much about how long a shark lives? The answer is that by studying these outliers, we are starting to realize that the limit of life is much more flexible than we thought. We used to think that aging was like gravity, an unavoidable physical force. Now, we're starting to see it more like a disease, or at least a manageable condition. If a bat can live 40 years and a whale can live 200, there is no physical law of the universe that says a human must decline after 80. The blueprints for a longer, healthier life aren't just theoretical, they are swimming in the ocean and flying through the woods right now. They are proof that nature has already solved the problem of aging dozens of times in dozens of different ways. We just haven't learned how to read the instructions yet. But even if we did learn, would we actually want it? If we could live as long as a Greenland shark, would we spend those centuries being productive and happy, or would we just get bored? If a bird's life is defined by the stress of flight and a clam's life is defined by the safety of the mud, what is a human life defined by? We are the only animals on Earth that are aware of our own mortality, and that awareness is what drives us to build, to create, and to love. If you took away the deadline, would the story still be worth reading? Or is the brevity of our lives the very thing that makes them valuable? We look at a mayfly and pity it for only having 24 hours, but to a mayfly, that single day is an entire lifetime. It sees the sun rise, it finds a mate, it fulfills its purpose, and it dies. It doesn't feel short to the fly, it feels complete. Maybe the problem isn't that we don't live long enough, but that we don't know how to measure time as well as the animals do. But let's go back to that heartbeat we started with. If you could count every single beat you have left, would you want to know the number? Or is there a strange kind of peace in not knowing if you're a mouse or a whale? We are currently living through a golden age of longevity research, where the gap between what is and what is possible is shrinking every day. We are learning how to listen to the genetic secrets of the oldest creatures on Earth, and what they're telling us is that the clock doesn't have to tick as fast as we think. We might not ever be immortal, and we might never outlive a clam in a mudflat, but we are the first species in the history of the planet that has the chance to decide for itself how long a natural life should be. We are no longer just passengers on the ride, we are starting to get our hands on the controls. So, why do some animals live longer? It's because they had to. They lived in environments that rewarded patience over speed or safety over risk. They evolved tools to fight back against the slow decay of their own molecules. They are the winners of a 4-billion-year-old lottery where the prize is more time. And as we sit here, in our air-conditioned homes with our complex brains and our deep-sea diving robots, we are starting to realize that we might be able to buy a few more tickets of our own. What do you think the correct length for a human life should be? If you could take a pill today that would let you live to be 200, but you had to live at the pace of a Greenland shark, would you take it? Or is there something about our fast, hot, frantic lives that you wouldn't trade for 1,000 years in the cold? Let me know in the comments what you think the limit should be, or if there should even be a limit at all. It's a question that scientists are asking more seriously than ever before, and the answer might be hidden in the eye of a shark or the heart of a bat. It is easy to imagine that we are the masters of this world, sitting at the top of the food chain with our technology and our medicine, Yet we are still bound by the same invisible threads of biology that dictate the life of a mayfly or a tortoise. We look at the 500-year-old clam and the 200-year-old whale and we feel a sense of wonder, perhaps mixed with a bit of evolutionary envy, wondering why we weren't granted that same gift of time. But in studying these ancient neighbors, we have learned that longevity is not a random miracle. It is a calculated investment, a biological trade-off that every species makes in its own way. We have begun to crack the code of cellular repair and genetic defense, peering into a future where the human warranty might be extended indefinitely. We are standing on the edge of a transformation where old age might become a relic of the past, a problem we finally learned how to solve. Yet, as we strive to stretch our seconds into centuries, we must remember that every extra year was bought with a specific biological price. Nature never gives anything away for free. We are finally learning how to stay in the game longer, but we are still playing by the house rules. Your heart has a finite number of beats, and the clock is ticking exactly as fast as it was always meant to. Every single cell in your body is currently deciding whether to save itself or let you die.